Inside every phone, laptop, and server on Earth, one silicon orchestra conductor turns electricity into computation. Billions of transistors switching in lockstep 10 trillion times a second. This is the central processing unit, and it's the strangest machine ever built. At its heart, a CPU does one deceptively simple thing: fetch, decode, execute. An instruction arrives from memory, is translated into hardware signals, sent to the arithmetic logic unit, and a result appears. Registers hold tiny pieces of state. A program counter marks our place. Every keystroke, every pixel, every neural network, it all reduces to this relentless cycle happening billions of times per second. A modern CPU is not one cycle, it's a factory floor. Pipelining overlaps multiple instructions, each in a different stage. Superscalar designs execute several at once. Out-of-order execution rearranges work to dodge stalls. Branch prediction guesses which way your code will turn, and it's right over 99% of the time. When it's wrong, the entire pipeline flushes. A single clock cycle is less than half a nanosecond. Light travels about 15 centimeters in that time. Main memory is agonizingly slow compared to the CPU. A single DRAM access can cost hundreds of cycles, hundreds of wasted nanoseconds. So the CPU keeps copies close. L1 cache sits inside the core, a few kilobytes, accessible in 2 or 3 cycles. L2 is larger, slightly further away. L3 is shared between cores, megabytes in size. Cache coherency protocols, like MESI, keep every core's view of memory consistent. Cache is where performance is won or lost. One core wasn't enough. Modern CPUs pack 8, 16, sometimes over 100 cores on a single die. Each one runs independently. Simultaneous multi-threading, Intel calls it hyperthreading, lets each core juggle 2 threads at once. But parallelism has limits. Amdahl's law reminds us, if part of your program is serial, no amount of cores can help it. Locks, atomics, and memory barriers coordinate shared state. Writing correct concurrent code is notoriously one of the hardest problems in software. The CPU landscape today is wider than ever. x86 still dominates desktops and servers. ARM powers every phone on the planet, and now Apple's Macs. RISC-V is the rising open-source challenger. Chiplets break monolithic dies into modular tiles glued together by high-bandwidth interconnects. 3D stacking piles cache vertically on top of cores. Moore's law slowed down, but through packaging, architecture, and sheer creativity, CPUs keep getting faster. Every year, for over 60 years,